earlier. I had some made mistakes in our early communication, but it's okay. People came back. Okay, so let's get started. So good morning, good afternoon, good evening, everyone. So welcome to your data webinar. Today is our great pleasure to our speaker Anta speaker with us from Université Marseille, France, CNRS, where she's currently working at. She has received all her education. I think most of her, especially her higher education in France, and currently working as a postdoc at the CNRS. Anta's work actually is quite interesting to us because it's a combination of both on the dynamics of the topography and the atmosphere science, also trace back to the geological history. Actually, that could be possibly be verified by the different geological records, as some of us are interested in. So with that, I will give the rest of time to Anta to talk about her work, and then please leave about like 10-15 minutes for discussion with our participants. So Anta, please.
I will share my screen.
Yeah, looks good.
Maybe. Yeah. Do you see it?
Yes, it's pretty good.
Okay, it works. So hi everyone, thank you for having me today. So I will present a study that I did earlier this year on South Asian monsoon evolution during the Miocene that we kind of study from modeling perspective. And I will try to show you what it can tell us about monsoon dynamics and the interaction with the geography. So those results are already published. This is the Sarr et al. 2022 paper in Nature Geoscience. You can find it on the QR code at the bottom of the slide or on my website. And this is work I've done during postdoc at CNRS and in collaboration with many of my colleagues in various French institutions whose names are displayed as well as the slides. So I will start by a small introduction on tropical Indian Ocean dynamics and its links to modern system of summer monsoon, because it will be the focus of my presentation. So the South Asian monsoon are associated with this biannual reversal of the cross-equatorial winds over the Indian Ocean. And during summer, that is the season that is displayed on this figure, the wind in the western part of the basins blow from the southwest to the northeast, north of the equator, transporting moisture toward continental Asia. Here, the one in black arrows, the left one, is the one I will be interested in during the presentation, and this is the low-level Somali jet. During summer, this pattern of atmospheric circulation is kind of coincident, not to say associated with strong precipitation over Asia, like India, Nepal, Myanmar, Bangladesh, a phenomena that we know as South Asian summer monsoon. This is the area in blue on the figure. From the oceanographer point of view, this peculiar atmospheric circulation forced a clockwise circulation in the ocean. This is the white arrows, with the cold water from the southern hemisphere being bring alongside African coastline through the Somali current, reaching northwestern Arabian Sea and then going down around South India types. Those surface currents are responsible for upwelling system generation along coastlines, like this is the pink areas and this is the Somali, Oman and southern India upwelling. During winter, the wind reverse and the Somali jet winds are directed from the northeast to the southwest, but I will not show that later because it's not the focus of the presentation. This summer upwelling is responsible for increase in biological activity along the coastline of Arabian Sea. This is the plot I display at the bottom, which show the cumulative increase in chlorophyll during summer season in this region. And the regions that are in orange in this figure are the region where we have a lot of biological activity during summer. And those regions also exhibit a strong seasonality, meaning that the summer activity is way higher than the winter one. And this is responsible for this like what we call biological boom. And this high productivity during summer is strongly associated with the monsoonal activity over the region. And this proxy of biological activity have been used over the past directly to infer the monsoon activity there, just based on the fact that at present day both winds, upwelling, and strong precipitation happen at the same season. At tectonic timescale, meaning over millions of years of Earth's evolution, the researcher did track the onset of the strong productivity in the region in order to kind of infer the onset of strengthening time of monsoon using oceanographic records. Here I display the kind of historical one. This is the record from Dick Kroon, 1991, on ODP sites 722 and 730 in Oman margin. This is the pink star in the map. And this record shows strong variation in the percentage of the foraminifera Globigerina buloides that is interpreted at the settlement or strengthening of the upwelling system around 11 million years. Here is the same site, but more recent study by Gupta 2015 that also show the bottom line, this increase in Globigerina buloides accumulation, but here they suggest that it starts around 13 million years, and it also starts alongside with increased total organic carbon accumulation in the cores. And both likely translate, as I just said before, an increase in biological activity at the site. And author interpreted that as the settlement of what they call Indian summer monsoon, or present-day Indian summer monsoon. Other proxies have been used to track this Miocene evolution of the monsoon system. Here is a record of Maldives Archipelago from Betzler et al. 2016. Here, the author used biogeochemistry proxies, such as the magnesium manganese calcium ratio that is interpreting at the strength of deoxygenation in the OMZ, that also is attributed to variation in upwelling activity tied to monsoon. And they show a strong increase in this ratio, around 13 million years, that they attribute to settlement or strong increase in the upwelling system there. All those records of biological activity in upwelling zone, in addition to other records as well in the Maldives region that show current variation, are interpreted at the settlement of modern monsoon somewhere during the Miocene. By modern monsoon, what the author referred to usually is the monsoon with modern atmospheric circulation pattern or strength. And those paleoceanographic records from the Miocene do look in contradiction with terrestrial records that mostly record the rainfall over the continent. This especially if we consider that at present day, both the wind pattern and the precipitation happen at the same time. And those records, for example, the one from Licht et al. 2014 in Myanmar using paleosoil chemistry, do show that modern-like monsoonal precipitation strength and seasonality are already present in the Eocene or even before. So we have kind of an apparent discrepancy on the monsoon timing, looking at winds pattern and rainfall. And this is kind of a long-term debate in the field of paleoclimatology, but also a science in general, as kind of the timing of monsoonal onset in Asia is crucial in the understanding of solid earth evolution in Himalayas and Tibetan Plateau region, especially because all those topography do interact with atmosphere dynamics. So what I did try in this study is to use the climate model to see if we can reconcile these two visions of the monsoon chronology. And to do so, I would investigate what happened to the upwelling system during the Miocene in those models and the relation with monsoon dynamic. So for those that are non-familiar with the paleoclimate modeling work, so the climate model we use are 3D models that enable to reproduce the functioning of the climate system, including the winds, precipitation, ocean circulation, or sometimes biogeochemistry in response to imposed forcing. And in this study, the forcing is geography, but it can also be CO2 levels, ice sheets, or orbital configuration. And we use this simulation to provide equilibrium climate, meaning that I do not provide any transient signal over several thousands or million years. The picture I display is the kind of results you get if you are able to plot them nicely. And this is the work from my Bristol colleague that is available on the Climate Archive website. So in this study, I use modeling framework that include a typical ocean atmosphere model, here the IPSL SEM582 model, So it's a Paris group model that is used also for CMIP, TIPMIP, PLIOMIP work. And I, alongside with this model, use an ocean biogeochemistry model, which is the PISCAS model, that I force with ocean dynamics fields from the coupled simulation. Having this biogeochemistry model enable me for once to compare directly with what the oceanographer shows, meaning an increase in biological activity and carbon cycle modification. So to investigate the question of monsoonal evolution, we did perform a lot of simulation with this climate model with various paleogeographic forcing, from the Eocene toward present, and here I will only show the Miocene part. The geography we use are based on Poblete et al. 2021 dataset. This dataset is super interesting because a lot of work have been put to try integrating all the recent data we have on Asian topography. So it's kind of useful to study monsoon dynamics. And for the late Miocene, I do use a plyomic lice setup with modification involving shifting the Australian continent southward and changing maritime continent configuration in agreement with geological data. And the idea in those simulations is to investigate systematically the link between upwelling activity, paleo productivity, and monsoon winds, plus looking at what happens to the precipitation dynamics. And the fact that we use realistic paleogeography matters because a lot of study looking at monsoon evolution do use modern geography and kind of move up and down topography, which might induce a different response to the climate system. And I will show using this peculiar setup and framework that we can for once find a way to reconcile the oceanographic and continental record and the model results. So here are some results. So on this slide, I display the variation in export production between the late Miocene and the early Miocene simulation. Export production is what we use in the model to track the amount of organic matter that might reach the seafloor. And it's kind of almost directly related in the simulation to the biological activity. What I show here is that the transition from the early Miocene to the late Miocene simulation do produce a strong increase in biological productivity alongside Oman and Somalia shorelines, almost what the data suggests. If we look at seasonal variation to better understand the mechanism driving this strong change in biological activity, so this is the right plot where I display the same variable, but this time with seasonal evolution from May to October months. Red is the late Miocene, blue is the early Miocene. And what you see here is that the strong increase in the late Miocene simulation is fully driven by this strong seasonal increase in productivity during the late summer. When in the early Miocene simulation, the productivity remained low overall the season and never increased. This productivity peak is fully driven by increasing nutrient availability associated with the settlement of the upwelling. That's what you can show on the two bottom plots. So in the middle, you have this increase in nutrient content on the red line that kind of mimic the pattern of productivity increase. And at the bottom, you have the velocity in the upwelling region. And you can see here that the late Miocene simulation do have a strong upwelling, almost similar to the present day one during summer, while the early Miocene simulation only have either no upwelling or a very, very weak one at the end of summer. So here's what's happening when we look at the water current. In dotted line, this is the nutrient content of the subsurface layer, and the full line are primary production. Red is still late Miocene, blue early Miocene. And here you can see that the higher productivity in the late Miocene simulation is sustained by the strong productivity in the subsurface layer, like above 60-meter depths. Where the paleo productivity in the early Miocene configuration is hampered at these depths. And this is directly driven by the depletion of nutrient in the surface layer in the early Miocene that you can see on the dot blue curve that is at 0 above 60 meters. And this is because surface circulation do not enable in this simulation to bring nutrient at this place. So no nutrient, no activity. So we are kind of able to reproduce what the data show, but upwelling is not enough. Like what we are interested in is monsoon dynamics. So I did try to look at map to figuring out the link between the upwelling signal and the simulation. Here you have a map showing the vertical velocity of the water in the subsurface that is, in the model, a good tracer for upwelling intensity. The left is the late Miocene simulation and the right is the early Miocene simulation. And you can see that in the late Miocene simulation, you have strong upwelling all along the coastlines. We can see clearly the Somali and Oman regions, while in the early Miocene simulation, there is no upwelling in the Somali region and really reduced strength of upwelling in the northern Western Arabian Sea. This apparition of upwelling in the late Miocene simulation compared to the early Miocene is associated with the settlement of the modern-like Somali jet with strong winds and winds that bend and are steered a lot toward the north, like almost at 20° north. This is the left bottom plot. So what you can see in this plot that display wind is that the strength of the wind is highly reduced in the early Miocene simulation by 6 to 8 meters per second. The wind remained east-west and never steered toward the north. And this results in suppression of the wind stress in the Western Arabian Sea region that is responsible directly for the lack of upwelling. In addition to that, what I show here is that the sea surface temperature during the summer season. And what you can see here is that this peculiar circulation that exists at present day and also in the late Miocene configuration enable cool water to be transported from the southern equator region toward African coastline, while in the early Miocene simulation, you have in replacement those super warm water from the Western Tethys Seaway that are brought toward this region. So these results kind of suggest that paleogeographic changes are responsible for a change in atmospheric dynamics in the Western Arabian Sea region during the Miocene. This because the only differences between these two simulations is paleogeography. CO2 is the same and so on. So what I wanted to do next was to try understanding what in those paleogeography triggered the signal I see. This because, as you can see here on the two maps, that the geography in the early Miocene configuration and late Miocene configuration in the Indian Ocean basins are really different. A lot of features are modified in between them. So to look at potential driver of simulated change, I investigate one by one the effect of these paleogeographic features on both wind system, upwelling, and precipitation. And I focus on features that I know have evolved during the Miocene time period based on geological data, and also that are known from the literature to drive change in the monsoon phenomena, because they have been studied mostly under present-day geographic configuration by my climate physicist colleagues. So in the late Miocene simulation, I will test the effect of closing the Tethyan Seaway, because it has been closed somewhere during the middle Miocene. And here I will more specifically focus on the effect of emerging land in this region. Then I focus on changing Iranian plateau and Zagros topography. This because even though timing of uplift there is highly controversial, it seems that data suggest recent tectonic activity probably during the middle or even the latest Miocene. And also I did try this one because it has been shown to have an impact on the monsoon dynamics and precipitation in the paper from Acosta and Huber 2020. In the early Miocene simulation, I did look at the influence of changing the configuration of Tibetan plateau width, but also changing the elevation of Himalayas mountain alone, as both have been widely invoked as triggering features for monsoon onset or a monsoon strength change at all time scales. And finally, I also did try to look at changes in Eastern Africa topography. So this one is kind of widely uncertain given that few quantitative data exist, but there have been rift activity during the Miocene there, and it should have somehow impacted the topography. And as I usually do not know the exact elevation of all the features at the precise timing, I perform what we call n-member simulation. So I, for example, fully remove the topography or fully increase it. so I can maximize the effect on the climate and better understand the physics of the changes. So here are the results. First, I will start looking at the Himalaya topography because it's kind of what people look at first. And I will display the result I got looking at winds, both strength and pattern over Western Arabian Sea, a pooling in the Oman region, and later precipitation. So here, let's start by the Himalayas. This is the middle plot. If I increase the topography in the Himalayas, what I get is almost no change in the jet. I mean, I increase the strength of the jet, but it still do not bend toward north. I'm not able to generate an upwelling in Oman region in a simulation that have no upwelling at first. Now, if I switch to African topography, what the simulation shows is that this topography is super important to be able to bend the winds, and it helps increasing a bit the strength of the jets. But I still have no upwelling in Oman, although I have upwelling in Somalia that was also absent in other simulations. Now, if I look at the precipitation in South Asian region in the same simulation, what I do show is that Himalaya increased South Asian monsoons precipitation during summer, but this is kind of expected results because this is what people have largely shown in paleoclimate modeling and climate modeling. And if I increase the topography in East Africa alone, on the other side, what I show in this simulation is that I also play somehow on the strength of precipitation in South Asian region, but I decrease precipitation here. This results on East Africa is kind of controversial because a lot of other studies using different models or different background geography setup do simulate an increase in precipitation in South Asian monsoon region while they change the topography of Africa. Now shifting to other more unusual features in the Middle East, namely the Tessian Seaway and the Iran Zagros. So what you can see here, starting from the right, is the late Miocene configuration with full strength of the jet. If I decrease the topography of Iran Zagros, I kind of keep this strong jet, but the strength is reduced. And I keep my Oman upwelling. Then if I open the seaway in the Western Tethys region that was closed in the late Miocene simulation, I almost do not change the wind, although they are more confined below 10 degrees north. And what I do, and what is super important, is that I remove the Oman upwelling, meaning that this upwelling state on and off is mostly fully driven by what happened in the Western Tethys region. Then looking at precipitation, so what I do see in those in those simulations is that if I am in a configuration when I have no Oman upwelling with the Tethys Seaway open, I do have strong seasonality of precipitation. Then if I close the seaway, triggering upwelling, I keep the same precipitation in South Asia, thereby showing that there are kind of a decoupling between the upwelling activity and the response of precipitation. Then if I increase the Iran and Zagros topography, I do intensify the upwelling at the same time as intensifying the South Asian monsoon precipitation. And this intensification of South Asian monsoon precipitation while uplifting the Iran Zagros is something that Paul Acosta already shown in his study, because like concluding that the presence of Iran Zagros kind of shelter the moisture coming from the Indian Ocean from the dry wind coming from Eurasia, and enabling more precipitation to fall down in the South Asian monsoon region. So one short reminder is what I have in this study is that in every case, I do have strong monsoonal activity in South Asian region, no matter the circulation I do have in the simulation. This is because moisture flux in the monsoonal region is not strongly modulated by any change I am able to simulate. And this kind of goes along, I think, with physicists' ideas that the monsoonal precipitation is a phenomena that are related to ITCZ and not a land sea breeze mechanism. So if I have to sum up, I would say that this study suggests that Himalaya and Tibetan plateau configuration and elevation, although they are big and superstar in the field, are probably not responsible for changes in monsoon dynamic in the Miocene. And by monsoon dynamics, I mean wind circulation. This probably also because the uplift that is really important for the monsoon happened probably before the Miocene. A weather change in elevation in this region is definitely important for precipitation dynamics because precipitation amount kind of scale with the height of the topographic area. This study also confirmed that Iran-Zagros elevation is important in controlling the strength of precipitation over continental Asia as well. On the other side, and I think that's new in this study, is that while they have been largely overlooked in most of the paleoclimate studies, the western boundary topographies are super important, especially for wind circulation. And we need to kind of be able now to provide better constraint on both East African topography evolution and what happened in the Middle East, because the chronology will matter for what we understand about the past monsoon evolution. And another result that is important here is that the Oman pooling is fully reliant on the Western Thaessian seaway states. And here it might also show kind of an impact of old change in Antarctic ice sheets modify the monsoon system, mostly because this Western Thaessian seaway close also due to sea level fall related to Antarctic glaciation. So it will provide kind of an indirect mechanism by which the ice sheets grow modulate the monsoon. So sorry, I have my first message is above. So I think this study shows a clear decoupling between winds and precipitation evolution over time, which was already what the data suggests. And this decoupling arises because both phenomena are responding to different paleogeographic control, with precipitation much more reliant on topography in Asia, while the dynamics of the circulation is totally reliant on all the other features surrounding the Indian Ocean. My second message is that I think we need to clarify what we mean by monsoon when we speak about that geological timescale. Do we refer to wind, especially when looking at paleoceanographic proxies? Do we refer to only precipitation, or do we look at both? And I think it will help having a better image, or at least a clear image of the monsoonal evolution, also help like discussing in between community and be sure we speak about the same thing at the same time. This is probably my conclusion with a few points that I think are very important. I guess that as paleoceanographic records suggest, modern like monsoon with present day circulation and precipitation pattern is likely a neogene phenomena. But it does not mean that changing wind at that time do have an impact of overall monsoonal precipitation over Asia. This means that upwelling also is probably not always a good tracer of monsoon rainfall activity on tectonic timescale, but it does provide good information of the state of atmospheric circulation. And the last point is that topography and physiography outside of Himalayas and Tibetan Plateau region do matter in monsoon dynamic, and we need to have proper constraint on those one. So this is my last slide, and this is the one I like the most. This kind of rely on my last point from the previous one, is that we really need, especially as paleoclimate modeler, to be sure that the topography we put into the model is what is rely on realistic constraint, especially when it comes to area outside of Himalaya and Tibet region that are under constraint, because all those topography will play a role on the dynamic of Indian Ocean and thereby on the dynamics of the monsoon. I really thank you for having me today. I can take some questions, and also feel free to email me in any case if you want to discuss or have more information.
Okay, thank you, Dr. Sarr. And now it's a question for our participants. So feel free to open your mic, or you could post a question in the chat. I'm going to read the question on your behalf.
Hello, Anta. Thank you for a very interesting talk and very, very cool figures. I need to figure out how to make figures, those globe figures that look like that. But yeah, very, very interesting simulations. So my question is related to what you just spoke about. It's mainly just like an implementation question. It looked like the resolution of the topography between the late Miocene and early Miocene was different. like it looks like the early Miocene was a little bit lower resolution. Does that have any impact whatsoever on the paleoclimate outputs?
I would say probably not. Maybe you refer to this slide.
Yes, exactly.
Yeah, so in the model, both geography have the same resolution, but here I probably use kind of higher resolution file that I have for the late Miocene to provide those nice figures, where for the early Miocene, I only had this model resolution geography. That's why they
Right.
look different.
Right. So if you were to, let's say, downsample the late Miocene to that of the early Miocene, probably wouldn't get too much difference. Is that your intuition?
I think it would probably do not make difference on the results, but if I kind of decrease the resolution of the late Miocene, which I do for the simulation, I would still have strong geographic difference.
Right, right. Okay, okay. And
like for example,
yeah.
For example, the East African topography is very low in my early Miocene, while it's full elevation in the late Miocene. Same Iran Zagros at half topography, and also like all the topography north of Tibetan Plateau are dampened in the early Miocene, where they have like almost full elevation in the late Miocene.
Right, right. Yeah, I can see that. And so kind of a related question, just I think many of us here don't have too much experience with these kinds of simulations. What would be the main differences between, let's say, a paleoclimate simulator and one that's trying to simulate, let's say, atmospheric dynamics on the decadal timescale? You know, things that we see for climate projections to the year 2100. I would guess that they have different sensitivities in terms of what are the main things that drive uncertainty in the outputs. But what are the main differences, like in terms of the dynamics that are being stimulated and the timescales that you're simulating them on?
So both models are, I mean, I use models that is also used to run the present day and future simulation.
Oh, okay. Okay.
So this is exactly the same model. The only difference is that this one has been a bit reworked so we can move the continents. But otherwise, all the physics is the same. Oh, I'm really sorry. My neighbor is...
We all have that problem. We can't hear it. I think Zoom is damping it out.
Yeah, I can move to another place. It's better, maybe. I'm so sorry for that. Yeah, go ahead.
Yeah. Okay, yeah. So you're saying that it's the same dynamics.
Yeah.
Okay, so
that's the same model.
Right. So in that case, can you say anything to what are other simulation factors outside of the geographic configuration that could possibly change the simulation outputs? Like what are the biggest drivers of uncertainty or the highest sensitivities in these kinds of models? Just for like some intuition.
Yeah, I would say like geography is the main problem.
It's the main thing. Okay.
Yeah, because we have a lot of uncertainty on that. Like we basically know almost nothing, and as you have seen here, like it triggers strong changes in whatever we simulate. Then we can of course change CO2 and Antarctic ice sheet. I did that in the paper, but the signal we simulate is really strong compared to what I have with geography.
Right. Okay, that makes sense. Thank you.
You're welcome.
Okay, next question, please.
Oh, I can read the one in the chat and answer. Right.
Yes.
So the question is, can the simulation take into account the erosional effects on the topography as well, thereby refining the resolution? I would say no. I mean, like I run this one simulation per geography, and there is no interaction between the climate and geography, meaning that whatever I simulate, the topography would remain the same. And if I want to kind of refine the resolution, including change in topography, it will not be possible anyway, because my model is kind of always reduced resolution. So I would guess it like it's just impossible to change that aspect at least. I hope I answered well to the question.
Okay.
Oh, hi. I just have a question. Yeah, thank you for the very interesting and very nice talk. And I'll also echo this, Brian. It's very impressive figures. So y'all have to learn how to make this kind of fancy figures. Yeah, I'm a geophysicist. So I'm just curious about, like you just mentioned, your model can predict the future weather, or you know, you basically predict, like, you know, the weather monsoon in back to Eocene. So I'm curious, you know, because Tibetan plateau is still rising. So I'm just wondering, could you share your thoughts, like what's the weather gonna look like in, say, a couple million years?
That's a super difficult question. I really don't know. I think like what matters, at least for the South Asian monsoon region, is really the height of the Himalayas more than what happened for the Tibetan plateau. And as soon as the Himalayas is growing, probably the precipitation would kind of increase in the region. Of course, I speak about like million of years of evolution there.
Okay,
And
so you're gonna expect more precipitations in that area.
But like maybe in 10 or 20 million years, if it's still increasing by that time.
Okay. Yeah, just curious. Thank you. Yeah.
Okay, any other questions?
Hello, me again. Yeah, I was slightly confused, or so yeah, slightly confused by the results showing, I guess, seasonal precipitation for all simulations were fairly similar. You know, they had they're showing the nice monsoonal cycle. So is the conclusion here is that basically all these configurations will generate the monsoonal precipitation. I think you also concluded that as well.
Yeah.
So in that case, the main point of your work was to look at the which configuration changes the dynamics. Is that correct?
Yep. Yeah.
Okay.
Yeah.
Like the wind patterns.
Yeah, that's what I focus on the simulations analysis, based on the fact that I wanted to study the interaction between upwelling and monsoon circulation.
Right.
And then I did look at precipitation, because this is, of course, what is of interest for people working on land, like geologists, biologists, and so.
Right. Okay. Right. And so, yeah, with the dynamics, you're able to reconcile the different proxies in a much more clear way. All right. Yeah. Okay. Yeah. Thanks. Yeah. Thanks for the clarification.
You're welcome.
So more questions? Okay, I think by that's thanks, Dr. Sarr again, by opening your videos, everyone, and then share a smile with our speaker today. And then we could turn off the meeting in 1 minute.
So thank you very much for having me there.
Okay, have a good day. Bye-bye.
Bye.